Good morning, everyone. I am Xiaoxing Wang, a doctor second-year student. So my topic is about historical weather reconstruction. So firstly, I have a question for you. Are you curious about the historical weather in ancient times? Unfortunately, before the 19th century, there are little instrumental weather database available due to the lack of measurement tools. However, we have some diaries recording historical conditions, and they are very important sources to reconstruct weather data. So the key issue of my research is how to get accurate weather data from descriptive information in ancient diaries. There is a historical weather database in Japan recovering the daily diary data during the period from 1750s to 1870s. I am going to utilize this database to reconstruct the weather during 1820s. So the main technique to reconstruct the weather is called data assimilation. What is data assimilation? Let's say this diagram. We already know simulations are based on modeling, so there must be some gaps between the model results and the real world. And the data assimilation technique can improve simulation accuracy by combining observations. And this is the so-called data assimilation. We can also say there is a basic assumption about normal error statistics. However, for cloud cover, most cloud cover didn't show the highly Gaussian distribution, and it will have negative impact on assimilation accuracy. So I used another method called Gaussian transformation, that is the GT, to transform the original cloud cover into a shape more resemble normal distribution as shown by this figure. Now let's say the performance of this GT method in idealized experiment in 2017. Here, the evaluation index I use is the reduction in root mean square error, and U wind speed and V wind speed are taken as examples. Because they are both three-dimensional variables, we can get the vertical distribution of reduction in root mean square error as shown by this figure. Blue line and red line indicate no GT and GT respectively. Zero values means no observations are assimilated, and positive values means the accuracy are improved. So we can say that the accuracy of U wind speed and V wind speed are both obviously improved by GT of cloud cover at almost all heights. Especially if we focus on sigma level 0.5, these four figures shows the horizontal distribution of reduction of root mean square error. So the left two figures shows no GT using original cloud cover. Right two figures shows GT using transformed cloud cover. Similarly, positive values shown by red colors means the accuracy are improved, and negative values shown by blue colors means the accuracy gets worse. And the number in each title shows the 2 months average of reduction in root mean square error. So we can say that at sigma level 0.5, the 2 months average root mean square error can reduce 8.3% for U wind speed and 5.3% for V wind speed, respectively. Now let's say the result for practical reconstruction. For data assimilation, I use totally the same initial conditions and boundary conditions as 1820s, but take 1995 as the target year in order to do validation using reanalysis data. And here are the results on 14 September. This figure is the weather map on that day, and these four figures shows different simulation results for sea level pressure. This figure are derived from the analysis database, which can be considered as reference. And this figure, the no obvious, means no observations are simulated. Here, this one is no GT and this one is GT. We can say from this result, for sea level pressure, the pattern approximates the real situation only when cloud cover after GT are assimilated, especially when we focus on the blue circle around Japan. So now we can conclude that the Gaussian transformation has the potential to improve assimilation accuracy and will be an effective approach in historical weather reconstruction. That's all about my presentation. Thank you for listening.